Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 43, we will continue with clustering, and the different concepts that we will cover will be on hierarchical clustering, and within that we will detail out the agglomerative clustering algorithm, and we will take the same grouping of urban zones problem and use and we will solve that using our agglomerative clustering. So, hierarchical clustering is where a dataset is divided into clusters following a tree-like structure, or otherwise known as a dendrogram, and this help us to interpret the clustering and the logic behind it easily. So, we can also determine the number of clusters, because whenever we are doing this way of clustering, then we have to decide that okay, how many nests or how many levels we need to go. And so, cluster size and numbers can be determined by cutting the tree at the correct level, right. So, if I want 3 clusters, I will cut it at a higher level. If I want 10 clusters, I will have to cut it at a lower level. Then hierarchical clustering can classify neighborhoods based on socioeconomic and land use characteristics, and this actually helps us to understand similar urban typologies. So, this is an example. It could be applied in many cases, and wherever we want clustering, but we also want to have some within clusters there are also other groups of clusters. If you want to identify that, this would actually help. So, there are 2 ways to go about it. One is the agglomerative hierarchical clustering, and the other is divisive top-down clustering. So, in agglomerative hierarchical clustering, what we do, it's basically a bottom-up clustering method. That means we start with each data point as a separate cluster, and then we progressively merge the closest clusters, and then actually that forms larger clusters, right. So, obviously the merging the matrix is distance. That means using distance as a metric, we can say that okay, these 2 clusters are merged, and then we can, based on our record, we can keep on merging. So, this is more or less flexible to a certain extent, and we don't require the number of clusters to be specified in advance, but once the clustering is done, then we can decide how many clusters we want, right. And again, for data with different arbitrary shapes and all, or cluster shapes, that also could be classified using this hierarchical clustering. In case of divisive approach, what we do is we start with one large cluster and then recursively split it into smaller clusters. We just go in the opposite way, but this is computationally much more difficult, takes more time and memory, and is very less common. That means it's not commonly used, right. So, most cases we will go for agglomerative hierarchical clustering. So, this actually produces something called a dendrogram, which I said it looks like a tree, and this is done so that we can interpret the clusters easily, and it is usually, this particular approach is suitable for small and medium data sets, and it can detect nested cluster structures because it's hierarchical clustering, and we can also have different distance matrices also employed. That means it is flexible. So, I can change, and accordingly the results will vary. So, over here you can see the image of a dendrogram over here and the data points which is leading to the dendrogram. So, what we do is each data point is considered as an initial separate, we can consider as a separate cluster, and then when we we say that well we set a distance, and based on the distance we can say that okay, this within these 2 distances, and then we can form smaller cluster. So, first we calculate the distance of all clusters are computed using a distance matrix. Whatever the distance matrix is, it could be depending on what number of features the data point has got, we have to decide on what matrix we use, and sometimes also based on the shape or the distribution and so on. So, that is either it could be Euclidean distance, that is straightaway distance using x and y, then Manhattan distance, cosine distance where direction is also involved, Mahalanobis distance, and so on. We have discussed this earlier as well. So, the distance matrix governs what's the criteria for considering which to how to form clusters, and the 2 most similar closest structures are first merged, and then we keep on merging that, right. So once we start with single points as cluster, and then the closest ones are merged, and then we keep on moving like that, right? So the distance matrix is then updated to reflect the new cluster structure, that is distance between zones based on population density, traffic, that's an example for it. And this process is repeated iteratively until all points are merged into a single cluster. So obviously, if I keep on merging by increasing the distance, eventually everything will become one cluster. So that means this allows us to help to understand that, okay, how at different distances things comes together, right? So over here you can see that we have got P1, P2, P3, P4, P5 and P6, right? So at the first stage P5, P6 gets combined. Similarly, P1 and P3 gets P2 and P3 gets combined. Then I increase the distance. Then P1 comes inside here. P4 comes inside. Then I keep on increasing the distance further between the clusters. Then the entire data set becomes one cluster, right? So in this way, we eventually leads to a single cluster or the hierarchical tree. So this entire way that we are doing this, merging, it could be also represented in form of a dendrogram or this tree structure, right? So the dendrogram shows the cluster merging sequence, that is at what distance these clusters merge. That means at certain distances we are seeing two clusters are merging together. So that is being plotted in this chart. So we see that the first clustering is happening between P2 and P3 at a distance of say 5. Then a little bit above 5.3 or 4, P5 and P6 is getting clustered. And then again a little bit above, like say around 6, we are seeing these two are, we are having another levels of clustering. So this actually shows that that based on the distance where the clusters is forming, I can also say that at distance, that means what should be the ideal number of clusters for this? Usually when there are large vertical jumps in the dendrogram, it indicates optimal cluster separation, and that should be the ideal distance, right? So what we can do is we can also determine the number of clusters you want by using this horizontal line. Over here I have cut it, horizontal cut lines determine cluster, number of vertical branches intersected says how many clusters are there. So if I cut it here, two branches are intersected, that means there are two clusters. If I intersect over here, there are 4 clusters, and so on. So the more distance is higher, the number of clusters will be lesser. So how do I determine all this? Now that we know how to measure distances, but how do I determine the distance between clusters, right? So that is where something called linkage methods comes in. So it measures how the distance between, how we calculate the distance between the two clusters, right? Because there are many points in the cluster. So between 2 points we can have a certain Euclidean distance or something we can compute. But because there are many points, then we have to determine also how do I consolidate between these different points. So the first method is single linkage or nearest neighbor, that is distance between the closest point of the clusters is considered. This is also known as the chaining effect. That is, instead of measuring all points, we take the within the two clusters which are the callest point. Then complete linkage, which is in this case the farthest neighbor is considered. That means the distance between the farthest points is considered. It is called compact clusters. Then there is the average linkage, that is average distance between all points of the clusters is considered. Then there is something called Ward's linkage, which is the most popularly used. What it does is it minimizes within cluster variance, right? So within cluster sum of squares, so we already know how to calculate WCSS earlier between the points and the centroid we have calculated this. So it minimizes the within cluster sum of squares, which is best for structured data sets, right? So this is the method, that is we try to find out at what delta E, that is this delta E value we will like to minimize. Now what is delta E? Delta is basically the increase in this is the within cluster variance after merging has happened, right? So when I am merging two clusters of sizes n1 and n2, and then what we are using is and between two clusters mu1 and mu2 are the two centroids, and these two centroid, actually we are finding the distance between that, and we are taking the norm of it, right, and squaring it. And then what is we are doing is that is we are finding the distance between the fetches of the two centroids, and we are depending on the size of the clusters, we are creating sort of a weight for this value also, right? And we will try to minimize this. That means we try to see that when delta E value is less, then it is suitable, right? So clusters with similar centroid and small variance are merged first, and so on. So again, to detail it out, WC, we already know this is WCSS, xi minus mu whole square, and data points on the cluster centroid. So when two cluster centroids mu1 and mu2 and sizes n1 n2 are merged, the new centroid shifts and data dispersion increases. So as soon as we are merging two centroids, obviously the dispersion will be more, and we are trying to reduce that, right? So mu1 and mu2, norm of mu1 and mu2 whole square is the distance between centroids, and if centroids are far apart, large variance increase happens. If centroids are close, we have smaller variance, right? So n1 and n2 divided by n1 plus n2 is the size weighing factor, adjust the variance increase based on the size of this cluster. So this is the weight given to that, for this size of the cluster. And the word objective function measures the increase in within cluster variance after merging of two clusters, and the algorithm selects the pair that causes the smallest increase, leading to compact and homogeneous clusters. So that means our job is to make sure that the dispersion doesn't increase when the merger happens, right? And that will lead to more compact and homogeneous clusters. And what is suited for continuous numeric and properly scaled data sets, obviously, and particularly for structured data, and where compact and homogeneous cluster patterns are expected. And Ward's method also relies primarily on Euclidean distance and not on other difficult, other measures. And it is sensitive to outliers, computationally expensive for large data sets, and may perform poorly for irregular non-spherical cluster shapes. So you know already that what to apply when there are irregular non-spherical cluster shapes. So we cannot employ this strategy over here, neither the k-means as well. So we are using the same data set as we have used earlier. So we have got different zones of the city, and each zone or that street segment and the related zone has got different parameters like characteristics of population density, traffic volume. You can see their units over here, and then our goal would be again to determine the right cluster using this particular data set. So this is the Python code. The first parts are common as usual, import NumPy, import pandas, import matplotlib, then simple imputer, standard scalar, then we are again importing a pipeline. Here we are introducing pipeline again, and then from scipy.cluster.hierarchy import linkage and dendrogram. These are the two things that we are importing, and also we are hierarchy import fc cluster, f cluster. So these two things we are doing it, right? We are importing these things. So this is what actually does the clustering, right? So this is the CSV file which we have which we are putting into the data frame, and once we have read that, we again check which are the numerical columns, and once we are if there are none, then we print that okay, numerical columns are not found. Otherwise we move forward and store the numerical columns, and then we can print the raw columns that we have done over here, and then we bring in the imputer and we replace the empty values with median. We also bring in the standard scalar to normalize the data set, right? If it is, and then once we are ready after normalizing and all, then we feed the data into this. We transform the data using the fit.transform _transform, and then we store the new data set in X. So now that we have the new data set, we can call the linkage function, where we are using word as the method, and and this value is stored in Z, and once we have done that, we can plot the figure using of course we can suggest the figure size, then we can plot it in the dendrogram, and where Z is one of the parameters which goes into that. And in the dendrogram, I can also determine that how many levels I want to show, where I can say the truncate mode we can use levels, and we are saying 6 level, and we also make sure that the leaf counts should be shown at each of these clusters, right. So this is what is happening over here, and then we can actually do the plot with the titles, labels, and then once the plot is done, then we can show the plot like this one. And then this what we can do is this FC cluster, that means over here, once this cluster, this labels HC, FC cluster Z, this particular line in the code, then what we do is it converts the hierarchical tree into flat cluster levels by cutting the dendrogram. So K clusters are formed, and the this levels underscore HC contains the cluster assignment for each data point, where levels typically range from 1 to K. So we can also print the levels after I have cut as per my dendrogram I am cutting, then only the data points could be assigned to a cluster. If I do not cut the dendrogram, how can I assign the data points to each of these clusters, right? So that is happening over here, and eventually we can store the result in df.out, and then we can we can save the data in this particular file as earlier, and then we can print this data as well. And once we can print the data, then we can print also the predictions, that means which cluster each data point belongs to, and we can first store it, and then we can also print that one out as well. So over here you can see the final dendrogram, how it has come, and then the data file is saved over here, and this is the assignment of the data, each data point into which cluster, right. So accordingly we can see over here which data point is going to which cluster, and we see that over in the dendrogram a big jump in linkage indicates a natural cut, good number of clusters, and cut possibilities based on a big jump, that means around 6 we are getting 2 major clusters, around 3 we are getting 3 clusters. So you can decide either it should be 2 or 3 clusters that you want, and then you can decide that, and once you decide that, then you can run the program to, or you can call the appropriate function to again assign this particular data points to each of these cluster, and then you can print it as we have done here. So these are some of the references we have used, and to conclude, hierarchical clustering provides an interpretable tree-based approach to uncover natural groupings in multidimensional data by progressively merging similar observation based on distance and variance criteria. Thank you.